Let us see an example today. An LTI system is characterized by h of z, which is given, the transfer function is given, and we have broken this up into different partial fractions. So, we can find out what are the zeros and poles from this equation. Okay. Now, three conditions are given as you see here. The first condition given is the system is stable, the second condition system is causal, and third condition the system is anti-causal. In all these three cases we have to find out what is the h of n for this equation. H of z is given, we have to find out what is h of n. The first case, let us write down the case one is the system is stable. The system is stable. Now, let us start working on this problem. So, given h of z and given the system is stable, I have to calculate what is the value of my h of n. Okay. And probably we can also tell what is the condition of the system. It is stable, it is given, h of n is then we can decide whether the system is causal, non-causal, and all those things can be calculated from this. From this, let us identify what are the poles we have. We have a pole at half and one other pole at 3. Okay, so we have a pole at half and another pole at 3. So, given these poles, we have to club this condition with the condition that is given, what is the system, whether it is stable or unstable, then we have to calculate what is h of n from that. Now, let us write down z is equal to half and z is equal to 3. So, these are the different poles which are available. Now, the system is, what is this? System is stable. So, where should be the ROC? The ROC, z must lie between 3 and half, because the system is stable. So, I cannot have a pole beyond the unit circle. So, the system is lying like this. So, system is stable. Now, how to calculate h of z is known. So, I have to calculate what is h of n. Okay. Let us write down h of z here again for convenience, that is equal to 1 by 1 minus 1 by 2 z to the power of minus 1 plus 2 by 1 minus 3 z to the power of minus 1. Okay. So, let us see this. This is h of z given 1 by 1 minus half z minus 1 plus 2 by 1 minus 3 z to the power of minus 1. Now, we have to calculate h of n from this equation. The condition here is ROC is given, the system is stable. So, then we have to find out what is the equation for your h of n. So, h of n can be written as from this equation half of n u of n. Okay. Because this is lying in between these two, it will be 2 3 of n u of minus n minus 1. So, this is your h of n from this, from that equation we have written. Now, this h of n, if you look at this is non-causal. If you look at the u of n and u of minus n minus 1, there is a clear indication that h of n is non-causal. Okay. Now, let us look at the second case, that is B. Now, let us see the case B. Case B is that it is given that the system is causal. So, okay, h of z is known for us, this is h of z, system is causal. Now, the ROC for such a system is z is greater than 3. Okay. So, whenever the value of z is greater than, that means the pole is lying outside the circle, the system is automatically unstable. Okay, because it is causal, I can write h of n as half of n u of n plus 2 3 of n u of n. Okay, this is my h of n, and the system is stable given this condition where the system is causal. Let us look at the third condition. What is the third condition says? The says its system is anti-causal. The system is anti-causal. So, let us look at this condition where the system happens to be the anti-causal. For a system, now for a system which is anti-causal, the ROC lies for z less than 0.5, that is this one. So, it is lying towards the this side. So, system is becoming anti-causal. Now, when system is anti-causal, what should be the h of n? H of n will be negative of the same value what we have written earlier, that is half of to the power of n plus 2 of 3 to the power of n, and because it is anti-causal, it will be lying in this area. Now, again if you look at this particular case and you look at this diagram, okay, this is the arrows, this is the pole plot, where are the poles lying? One pole is lying at 0.5, other pole is lying at 0.3. Okay, now this is less than 0.5 and the system automatically becomes unstable. So, now this particular example is a demonstration of how we can decide the system condition, whether it is stable or unstable, causal or anti-causal. Then we are also able to calculate from h of z directly what is the h of n. Let us see another example. Now we have to find out the response of the system. Okay. Y of n is given 5 by 6, y of n minus 1, minus 1 by 6, y of n minus 2 plus x of n, where x of n is also given as delta of n minus 1 by 3 delta of n minus 1. Now we have to calculate what is y of z. Okay. From that, what is the response of the system. Now, if you look at this, the system is like this. Now we have, this is my output, okay, this is my function, okay, transfer function, and this is my input. That means, if output is taken as the z transform y of z is equal to h of z multiplied by x of z. Now, from this we have to calculate what is h of z, what is x of z also. So, we can write directly from this equation what is h of z. So, h of z can be written as, from this it will be equal to 1 by 1 minus 5 by 6 z to the power of minus 1, okay, plus 1 by 6 z to the power of, this is n minus 2. So, this will be n minus 2. Now, you can factorize this. When I factorize this, I can get this as equal to 1 by 1 minus 1 by 2 z to the power of minus 1 into 1 by 1 minus 3 z to the power of minus 1. Now, from this I can find out where are my poles. So, let us say this is my pole, two poles are there, so Z1. So, Z1 is half here pole and the other pole exists at this place, that is Z2 is equal to 1 by 3. So, now we have two poles, one at half, the other one at 3. You can actually draw a plot indicating these two. Now, x of n is there. So, we can write x of z here. X of z is delta n, this is 1. So, 1 minus 1 by 3 z to the power of minus 1. Okay, if you look at this equation and this equation, there exists a 0 here at 1 by 3. So, there exists a pole at 1 by 3. So, there is a 0 pole cancellation here. So, one pole is getting cancelled because of the presence of 0 at the same place. So, 0 is cancelling one pole. Now, what is y of z? We have already written y of z is equal to h of z x of z. If you multiply this, then I will get y of z is equal to 1 by, because this term is what is getting cancelled. So, what left is this, that is 1 minus 1 by 2 z to the power of minus 1. So, this is my y of z. So, inverse I will get y of n is equal to half of n, okay, u of n. So, this is my response in this time domain. Okay. So, this half of n to the power of u of n. Okay. So, this is particular example where we have seen that a pole under 0 here which existing at the same place are getting cancelled. So, this is an example which demonstrate the 0 pole cancellation. Now, let us look at, because we are solving so many examples, let us look at some common Z transform pairs. Some common Z transform pairs are like this. This will help us in directly finding out the inverse or the actual Z transforms. Okay. Now let us look at the first signal delta of n. It's having a Z transform 1 and the ROC is all Z. Then the second signal U of n will have 1 by 1 minus Z to the power of minus 1 where Z is greater than 1 ROC. Third, A to the power of n U of n. This we have been invariably using throughout our discussions earlier. It is having a Z transform equal to 1 by 1 minus A Z to the power of minus 1 where the ROC is Z greater than A. Okay. Similarly, when I multiply A to the power of n U of n in the earlier formula with a factor n, then the Z transform will be A Z to the power of minus 1 by 1 minus A Z to the power of minus 1 whole to the power of 2, and the ROC there is no change and Z is greater than A. Similarly, if you look at the other signal, let us say that is equal to minus A to the power of n U of n minus n minus 1, then it will have a Z transform that is equal to 1 by 1 minus A Z to the power of minus 1, which is same as A to the power of n U of n, because it is minus A to the power of n U of minus n minus 1. So, we are clearly mentioning there. So, both of them will be same, but the only difference is that ROC was greater than Z A there in earlier case. Now, the ROC will be less than A in this particular case. Similarly, when A to the power of n U of minus n minus 1 is multiplied by factor n, then it results in the sixth serial number, which is equal to minus n A to the power of n U of minus n minus 1. That will be equal to Az to the power of minus 1 minus Az to the power of minus 1 whole square, and the ROC earlier in the case where it was U of n, it was ROC was greater than A. Here Z is ROC Z is less than A in this particular case. Continuing this, there is another signal cos omega naught n U of n, that is given by 1 minus Z to the power of minus 1 cos omega naught divided by 1 minus 2 Z to the power of minus 1 cos omega naught plus Z to the power of minus 2, where Z is greater than 1. That is, the ROC is the region beyond greater than 1. Similarly, if I can get the sinusoidal function, the Z transform will be sin omega naught n U of n. For this, Z transform will be Z to the power of minus 1 sin omega naught divided by 1 minus 2 Z to the power of minus 1 cos omega naught plus Z to the power of minus 2, where Z is greater than 1. Okay. So, you can just see this small difference between the Z transform of a cosine function and the Z transform of a sinusoidal function. Then coming to the next identity, A to the power of n cos omega naught n U of n, the formula will be 1 minus A Z to the power of minus 1 cos omega naught divided by 1 minus 2A Z1 Z to the power of minus 1 cos omega naught plus A square Z to the power of minus 2. So, the presence of A here is the continuous multiplication, as you see in the numerator and the denominator. Similarly, A to the power of n cos sin omega n U of n will be equal to A Z to the power of minus 1 sin omega naught divided by 1 minus 2 A Z minus 1 cos omega naught plus A square Z to the power of minus 2, and the region of convergence Z is greater than A. So, if you remember mostly all these 10 identities, it will be easy for us to directly step into the examples or problems, and then we can find a solution at a very faster rate. Okay, let us see another example. Here, so far what we have done, so far we have tried to plot pole zeros from a given equation or a given system transfer function or the given system. Now, here what is it we have to do? We have to calculate the system function given. Okay, we have to the question I will read for you: determine the Z transform and the signal that corresponds to the pole zero plot on the figure shown below. That means we have to find out what is the Z transform, what is the signal. That means if I call the signal as x of n, I should know x of n, and also I am supposed to calculate x of z from this given plot. If you analyze this plot, okay, this is the pole zero plot. If you analyze this, if you look at this, I have two zeros. Okay, so number of poles are how much? Let us say m is equal to 2, and they are z. Okay, z1 is existing at 0, and another one z2 is present here and is given by r cos omega naught. Okay, because this is existing at this particular point, and r is the radius of this circle, and if r is tending towards 1, it becomes unit circle, but r is not given as 1, so we have to retain that r as r itself. Similarly, if I look at poles, there are two complex poles, conjugate poles. So if I call them as n is equal to, I have two poles P1 and I have P2. Okay, so this is given by r e to the power of j omega naught, and the other one is given by r e to the power of minus j omega naught. So now we have, from the figure we have identified what is a 0, from the figure we have identified the number of zeros, from the figure we have also written where does these zeros exist, and similarly for poles also we have calculated on similar lines. Now next, what is it we have to do? Now let us first start with the Z transform, and from the Z transforms let us get back the signal, because already pole zeros are there, it is easy for us to write down what is x of z. Now we all know x of z is given by a certain scaling factor g, because we have two poles, this will be z minus z1, z minus z2. If it is m is equal to m, that means m number of poles, then that equation will go on z minus 1, z minus 2, z minus 3 up to z minus n. Similarly, the number of poles I have are two poles, z minus p1 and z minus p2. Now let us substitute what are the values which we know. So I can write this as g is a common, it is scaling factor, it can be 1 also if you want. So here z is existing at 0, so this will become z, okay, and this is z minus, how much is this? This is r cos omega naught, okay, divided by, where is this pole existing? This pole is existing at r e to the power of j omega naught, and this is existing at r e to the power of minus j omega naught. Now what you can do is you have to simplify this. Okay, after simplification, what I can write down here is this, I can write as equal to g into 1 minus r z to the power of minus 1 cos omega naught divided by 1 minus 2 r z minus 1 cos omega naught plus r square z to the power of minus 2. Okay, we have just now seen different identities and their equivalent x of z's. From that, what is it we have to do? Now we are getting x of z. This is my x of z. Okay, so go and look at the table. Then I can calculate what is my x of n from the table. So I will get this x of n as equal to, g is again same, g can be 1 or it can be any value, that will be equal to r to the power of n cos omega n naught, okay, u of n. So what is it we have done in this problem? We have got a pole zero plot. From the pole zero plot I have identified where are my zeros, where are my poles. From this I have written x of z by taking a generic equation. We have identified how many number of poles or how many number of zeros we have done. Then we have written that, we have simplified it, and finally we got the answer x of n by looking at the table which we have. Either we should remember fully or we should make a references to it and then writing the answer. But it is always better you by heart or remember those 9 or 10 identities permanently. Now let us look at another problem. Okay, in this example, what is that is given is a differential equation has been given and we are asked to find out what are the system poles and zeros. So let us write down the first what is h of s from this. Okay, because now we are writing in terms of Laplace transform. Okay, so far we have looked at Z transform. Because of the involvement of a differential equation, let us quickly shift to Laplace transforms and then write down what is the h of s from this, and from h of s I can of course plot my poles and zeros. So let us write down what is h of s from this. Okay, h of s. Okay, let us write down first this equation. So this is a double differentiation, so that will be s square. Okay, this is a single differentiation, so I can write this as phi s, and this is no differentiation, so that will be S6. So this is what we got. And now there is a single differentiation this side, so that will be 2s plus 1. So we are able to directly write what is h of s from the difference equation because of our earlier knowledge in Laplace transforms. Now let us just simplify this to find out where does a pole exist or where does a 0 exist. So I can write this in terms of 2, I will take common, so this will be equal to s plus half, okay, and this I will factorize. So I can factorize this as s plus 3 into s plus 2. Now for further simplification, what I will just do is I will write this as 2 of s minus of minus half, okay, divided by s of minus 3, s of minus 2. Okay, from this it is very clear where does a 0 exist or where the pole exists. Where does the pole 0 exist now? The 0, 1, 0, let us say that is Z1, exists at minus half. Okay, how many number of poles we have? We have 2 poles, one exists at minus 3 and one exists at minus 2. If you look at these 2 poles, these 2 poles are real poles. These are the real poles. So we have this, that's how we have calculated both zeros and poles from a given equation. Let us look at another problem. The problem is given like this. So what are the different poles given? It is given as this is equal to minus 1 plus or minus j2. Now in this problem we have P1, P2 given, a real 0 is given and a scaling factor k is 3 is given. Now from this we have to find out what is the differential equation. So it is a reverse of what we have done in the earlier problem. Earlier problem we have from the differential equation we have calculated h of z and all those things. Now here it is a simple where I have to write first h of s. From h of s I can directly write my equation, differential equation. So let us write down what is h of s. H of s is given by k into s minus z, because there is only one 0, s minus p1 and s minus p2. So this I can write as, for us k is equal to how much? 3, and where is my 0 existing? At 4. So this will be equal to s plus 4 divided by, this I can write as, there are 2 poles which are existing at this. So this will be s plus 1 plus j2 into s plus 1 minus j2. Okay, so let us expand this. So this will be equal to 3 into s plus 4 divided by s square plus 2s, okay, plus 5. So this is my h of s. Now from this h of s I can write down what is my differential equation. So differential equation, this is s, so it will be s square, so it will be d square y by dt plus 2 dy by dt, okay, plus 5y is equal to 3 du by dt s square. So we have written d square y by dt plus 2 dy by dt plus 5y is equal to 3, s is the 3s, so that is 3 du by dt plus 3 into 4, that is 12u. So this is my differential equation from the given transfer function. Because it is a differential equation, we have obviously used Laplace transforms.